Welcome, everyone, to the second of my series of 4 talks. This talk is really a tutorial level talk on predicative programming. I see several people here who really don't need to be here because they really know this material, some of whom we've even taught this stuff. So, but anyway, you're certainly welcome. So I should start by saying, what is predicative programming and why should you even care about it? Well, it's one of many formal methods, or maybe I should say several formal methods. Formal methods refers to making proofs about programs or programming. You could make these proofs after usually the proof is to prove it's correct according to some specification. And you could make these proofs after you've written a program, but you can also make these proofs while you are writing the program. And that has the advantage that if each step you make in programming is proven correct at the time you make it, then you don't risk building the rest of the program on a wrong earlier step. But of course, there are also programs written without the benefit of formal methods. And we do have to be able to verify programs after they're written as well. So there are several quite well-developed kinds of formal methods. The particular one that I'm showing you is the one that the American Presidential Science Advisory Committee, advising the US President, I suppose, says that this is the best of the formal methods. So I don't know why Obama needs to know that, but anyway, that's the one I will be talking about. So in predicative programming, the first thing you have to do is decide what is of interest to you. There's no right answer to what is of interest to you. Here are some of the possibilities. You might be interested in the initial values of program variables and final values, or intermediate values, or other things, probability distributions and communications and so on. So what you do is you have to introduce a variable for each quantity that is of interest. And I'm just going to take a very simple beginning, and that is suppose that initial values of program variables and final values of program variables are of interest, just to start off simply. Okay, now a specification is a Boolean expression in those variables. Why a Boolean expression? Well, when you test something against a specification, either it satisfies it or it doesn't. That's 2 possibilities. That's why it's a Boolean expression. When I say Boolean expression, I allow sub-expressions to be any type, not necessarily Boolean, variables to be of any type, any operators, quantifiers, they're all acceptable, just so long as the overall expression is of type Boolean. Okay. Now a program, well, that's also a specification, because what we're specifying here is computer behavior. We're specifying what the execution should be of a, that's what or description, I could say, describing what the execution should be. The difference between a specification and a program is just that you can give a program to a computer and get the execution. So it's an implemented specification. Okay. Now, okay. So if you were just talking about the initial and final values of variables, then this is the formula for implementability of a specification. You have no control over the input, or at least the computer has no control over the input it's given. Its control is over the output that it provides. So this just says whatever the initial input values are, there must exist some final output values that satisfy the specification in order to be implementable. And the next definition is really the central definition for this kind of programming. One specification P refines another specification S just means that all executions satisfying P also satisfy S. So it's just implication. Now I want to look at a particular specification, the simplest perhaps, that says all final values equal the corresponding initial values of all these variables, whatever your variables may happen to be. So if your variables are x and y, it's x prime equals x and y prime equals y. It's a specification that's particularly easy to implement. That is, the computer doesn't need to do anything at all, just nothing satisfies it. Leave it alone and the final values will be just like the initial values. So that can be a programming notation. The next one is an assignment notation, x gets e, which is not much more complicated. It just says that the final value variable x is the same as the value of expression e, and all other variables, whatever they may be, are left unchanged. It too is very easy to implement, so I'll count it as a programming notation as well, as long as you know how to store something somewhere. Okay. The next one I'm going to introduce is just a familiar if-then-else, should be an if-then-else in every programming language. So it's a specification notation. S and R could be any specifications at all. But if they happen to be programs, then this notation is also a programming notation, it's also a program. And as a Boolean expression, well, B and S, or not B and R. Or equivalently, since just Boolean algebra, it could be B implies S and not B implies R, or anything else that's equivalent. Okay. And one more, and it is sometimes called sequential composition or dependent composition. So S and R are arbitrary specifications, and this describes computer behavior that first satisfies S, and after that satisfies R. But if S and R happen to be programs, then this is also a program. It just identifies the final values from S with the initial values from R, for R. There's lots of laws that you could prove from these definitions. I'm not going to burden you with all of them right now, but just mention one that's particularly useful called the Substitution Law. It says if you have an assignment, x gets e, followed by any specification, that's the same as the specification, but for x substitute e. I'll be making use of that. Now, if you've learned any formal methods at all, just a little formal methods, probably it's what's usually called Hoare logic, or a Hoare style of specification and proving. Now, this is from probably the first paper on formal methods, 1969. And for a large part of the world, it seems to me, they think formal methods stopped there. And when you read any textbooks, introductory textbooks on programming, there's usually a small inadequate chapter on formal methods that uses this style of specification, in which there's a precondition and a postcondition. I mean, not even Tony Hoare has used this for a very long time. He uses predicated programming, but the textbook writers just dutifully copy from the previous textbook and don't seem to make changes. In this style, maybe some of you know it, so I'm going to compare with this just since that's the one that's usually taught. Well, you could write the same thing in predicative style this way. Pre implies post, and that's implied by the block, because the block, it could be a block of a program, in which case it is a Boolean expression, and so it can fit there as the antecedent of an implication. Could be arbitrary specification as well. It doesn't have to be program. And anything equivalent. For example, pre and block implies post. The only reason I wrote it this particular way is because I can now identify pre implies post as being a specification and block as being an implementation of it. And in between, I have is refined by, or is implemented by, if you prefer. That specification is refined by, implied by, implemented by the implementation. Okay.
In the post condition, in the predicated style, you have to rename the variables to the final version. Right, in the post, in predicated style, the variables are prime, whereas in oral style...
Oh, that's true. Thank you. That's quite true. In the original horse style, the post condition, the variables in the post condition were not primed. But if you prime them, because they're in the post condition, then this is right. Yes, thank you, Albert. Okay. So the implementation, as I mentioned, could be a block of program statements, but it could just be an unrefined specification waiting to be refined. Or it could be a mixture. And that's really useful because you can't do it all at once. This is really stepwise refinement. You begin with a specification, you do some refinement, and in the end you end up with a program, but in the middle you've got some mixture. And there's no harm in the mixture of program and specification because they're all just Boolean expressions. Okay, it could be, a specification part could be, as in the old horse style, a pre-post condition pair like that. Or it could be a disjunction, for example, saying I have a choice between two possible things for the outcome. Well, it could be a disjunction of pre-post condition pairs, if you like. It could also be a conjunction, and that's really, really useful because you can't usually write an entire specification all monolithically as at one particular time. You really want to write specifications in parts. And the good thing about here is that if you prove correctness for one part and prove correctness for another part, then for free you get correctness of the conjunction. So you don't have to separately prove the conjunction. It could be a conjunction of pre-post pairs, but a little bit of warning here. This is not the same as collecting the preconditions and collecting the post conditions into one Hoare-style specification. So in fact, this is definitely a generalization of the old Hoare style. Okay. In general, it could be any Boolean expression whatsoever, as long as it's implementable. Now, also, we don't need new rules for every new programming construct. The rule is always just implication. That's all you're proving all the time. So that's, again, a reason for generalization. I'm going to show you more about that as we go along. Okay. Refinement is always implication. Here's my first programming example. It's not going to be, the solution I'm going to give is not even the best way to do a cube. It's just a good way to show predicative programming. So the problem is make the final value of variable x be n cubed, where n is some natural number. And to make the problem a problem, I will disallow multiplications and exponentiations in the solution. Okay. So one way to refine this, perhaps a fairly obvious way, might be x gets n to start with, and then multiply by n again, and then multiply by n again. Well, great. Part of this is program. This part here is program. But this part isn't, and this part isn't, partly because of the primes and partly because of the multiplications. So I still have some refining to do. I have to refine this part and refine this part. But before I do that refining, I really ought to prove that I have made a correct refinement already. Yes, Hugh.
Why did you choose to put one prime on two of them instead of two primes on one or no primes on any of them?
Well, so are you asking why is there a single prime there?
And in the one to the right.
And in the one to the right.
Yeah.
Well, reading this little piece of specification right here, I want the final value of x of this little piece here to be the initial value of this little piece right here times n. Same for here. Or to put it another way, unprimed and primed are local between semicolons. All right?
So do you really mean what you wrote
Yes?
there? You're not changing x. Yeah, he is changing x.
Yeah.
But at the semicolon,
X,
nowhere else.
the final value of x here is not equal to the initial value of x here. It's x times n. And then again, I'm going to multiply by n. Okay.
By this time, x is no longer a mutable program variable. It is a mathematical variable.
Between the semicolons.
Right.
But in it,
No. In, right, between the semicolons.
Right.
Or in the specification.
Okay. There could be lots and lots of questions. And I want to answer questions. But there's always a trade-off between that and getting as far as I want to get in the talk. So what I want you to get out of this talk is not something very detailed. What I want you to get, because all of that's in a book, and I can point you to the book, and I will. But what I want you to get out of this talk is what are the ingredients of predicative programming? What generally is going on there? So, to answer Charlie's question a little better, I'm about to prove that it's correct. I'm not going to show you proofs in detail either. I'm going to save time by not showing proofs in detail. But what you can see from this quickly is simply how long it is. It's short. And looking over here, you can see what's involved in the proof. Well, a one-point law and some substitution. The substitution is particularly easy to see. It says replace x by n in here. And so anyway, without going through proofs in detail, all of which you can check later at your leisure, I just want you to see how easy or difficult they are. And in almost all cases, it's very easy. Okay, so having proven that, I can go on and refine this next piece. Well, it occurs twice, but I only have to refine it once. So let's refine that. Okay, once again, you might have doubts as to whether I have refined it correctly or not. Lacking multiplication, I've made the decision to accumulate a sum. And I'll start with 0, and I'll keep adding something until I've got a cube. So moving along rather quickly, I'm afraid, I have to prove that to show that I've made a correct refinement. And okay, starting with the right-hand side, it's just two uses of the substitution law, replacing x first by 0 right here, and then replacing y by x right here, and I get this. That was one use of the substitution law. That's two uses of the substitution law and a little bit of simplification, and I have proven that refinement. Not difficult. And now I have something new to refine, and it's sitting here. So I'll refine it. Well, there's not just one right way to write a program to do something, and this is just one of possibly many ways I could have refined that. So if y is 0, well, look over here. If y is 0, it says x prime equals x. In other words, there's nothing more to be done. We're done. OK says there's nothing more to be done. And otherwise, well, I'm going to add another n, decrease the count of n's to be added, and repeat. Now I said repeat right there because that's the same specification that occurs right there. In any case, I should first prove it. So I can simplify the else part by two uses of substitution law right there and simplify that. This might be a bit quick, but still. Next time, I can use the definitions of if then else and of OK. And finally, I will be proving that each disjunct implies the left-hand side up here. And whether you follow that or not, you see what the ingredients are. You see how easy or difficult it is. You see how long the proof is. You see the style of proof. That's the important point here. Okay, so looking at, I'm done. There's nothing more to refine. Nothing that is unrefined here. There's two ways I can look at this. One way is the way the prover looks at it. And the prover says, well, this is 3 implications to be proven. And in proving these implications, well, this is fine. This is a Boolean expression. This is a Boolean expression. But this part, what's that? Well, it's just another Boolean expression in disguise. Programming parts are just Boolean expressions in disguise. So the prover treats programming parts as Boolean expressions and makes the proofs, just as I've done. But the other way of looking at it is, what does the compiler do with this? How do you get it executed? Well, to a compiler, the program parts are fine. X gets in, fine. All right, but what's this? And what's this? Well, to the compiler, the specification parts that need refining, they're just identifiers. To help you see it the compiler's way better, let me just reduce those identifiers to single letters, P and Q. All right? So that's more or less what the compiler sees. And it's immediately translatable into any programming language. So I've used C here. It's just transliterating into that programming language. So it's just what we have above, translated into C. Now, in case you don't like all these calls, this is a call to something called Q, and a call to Q, and a call to R here, call to R. And you might not like them because, for one thing, the compiler might do a terribly poor job of, the C compiler might do a bad job of compiling that. It might think it involves stacks or something, but it doesn't. So you might want to replace this R, for example, with a goto. So having replaced R with a goto, I get rid of a call. Now, you might have learned somewhere that gotos are not good. But I would like to remind you that this part down here is not my program. My program is up here. That was my programming. This is my object language, my assembly language, if you like. Okay? What's up above gets automatically translated to something like what's down below, or whatever your object language or your assembly language might be. If you still don't like it looking like this because of the goto, you could, of course, replace that with a loop if you want. I mean, it's equivalent to this while loop. I don't know why you would want to do that, but you could. And you could get rid of the 2 occurrences of Q, if you like, just by replacing them by the body of Q right there, ending up with that. But all this is, as far as I'm concerned, optimizations made by a compiler or something past the concern of the programmer. Okay? So you get execution from what's up above. Charlie? Yeah.
So whether you want to say this is a program or specification, it's well defined because it halts, assuming n is non-negative integer. But why does it halt? I mean,
All right, I'm just about to get to that, right about now. Okay. All right, so just back to the program that we had there, and putting back the specifications into what I had there, I'm now going to talk about execution time. And in order to, whatever you want to talk about, you can talk about it. You just need a variable for that. So all I need to do is add a time variable t, and I can talk about execution time. You might be interested in real time, and that's fine, in which case you're going to need to know a little bit more. You're going to need to know what platform this is being run on and execution times of things and so on. That's fine. There's no way around it if you really want real time. You might want a little less. You might be satisfied with upper and lower bounds for execution time to make it a little bit looser or easier. Or time could be measured by counting some operations, whichever operations you think are worth counting. There's not one right way to do it. What I'm going to do is count iterations, just to show you how this time stuff works. And to count iterations, what I have to do is include a time increment inside any loop. Okay, so let me spread it out a bit just to make room for the time. That's the same thing I just had. I just spread it out a bit. And right there, I'm going to put a time increment to count iterations inside the loop. Okay? Okay, so in the specification back here, well, what will I say about time? This is a particularly easy one because the time is incremented just exactly as y is being decremented. So it seems that the time should be, and it's being decremented to 0, so it seems that the time should be y. So I'm going to say, as part of my specification, the final time is equal to the initial time whenever the computation starts plus y, or if you prefer, t prime minus t is equal to y, to say that the execution time is y. Now, I should prove it, and I don't want to go through the details of the proof. I just want to show you that the proof didn't actually get any longer in terms of number of lines, and the steps in the proof are the same steps that they were before previously. So the proof is no more difficult, but I do have to take care of time. And that's done in exactly the same way as I took care of proving the result variables before. All right, so once that's proven, well, that specification at the bottom left, that was called from right there. So it was supposed to be the same specification as there. So I'll just have to put that same time specification there. And now, for proving this refinement, I'll start with its right-hand side. And same as I did before, substitution law twice and simplify. I find out that the time on the left side should be x. So now I know what to fill in right there. T prime equals t plus x. And since that was called from up there, I should put the same thing right there. And now I'm going to have to prove that the first refinement there, all right, I've skipped the steps in there, but it's not long, and take my word. It says in the end, x prime equals n cubed and t prime equals t plus n squared plus n. So now I know what to fill in right there. Well, I never would have guessed that to start with. If you'd asked me the execution time, I wouldn't have said, oh, obviously it's n squared plus n. But I calculated it. I calculated the execution time. So the calculation tells me what it is. Now, Charlie wanted to ask about termination. So I've just calculated the execution time as being n squared plus n. That tells you that the execution terminates. It tells you more than that the execution terminates. It tells you that it's time n squared plus n. Okay?
Is n negative here?
No, n's a natural number. That's why I picked the letter n. Yes. Okay. I'm going to now solve n squared plus n isn't very good for cubing, even adding up a sum. So now I'm going to try the same problem again, just slightly differently. And this time I'm going to try a different strategy in order to get a linear execution. So I'm going to suppose I can say if n equals 0, then x gets 0, because that's obviously if n equals 0, x gets 0 solves the problem. Else we want to decrease n by 1 and repeat. That's the sort of template here in order to get linear execution time. Okay, so, but this this else part can't be right. It's not what we want. I mean, if I replace n by n minus 1 in here, I haven't got a solution. I've got n minus 1 cubed, not n cubed. So that can't be right. Obviously, I'm really going to have to accumulate a sum anyway. So I'm going to have to say x gets x plus something to correct. X plus what? My problem is to get from n cubed that I'm given right there to n plus 1 cubed in the body. So what I want to add right here is the difference between n cubed and n plus 1 cubed. That's what I need to add in that space. Right now I'm saying it informally. I have to prove it, of course. But that's what I want to fill in right there. So I just do a little bit of algebra, and it says what I really need to fill in there is 3n squared plus 3n plus 1. But I don't have multiplication. I don't have exponentiation. So I can't fill that in right there and get a program. But what I'm going to do then is just say x gets x plus y. I'll introduce a new variable y, and y is going to magically, wonderfully have exactly the right value that I want. Why? Well, because I'm just going to change the specification up here to say that the value of y after that specification is exactly the right thing to be added to x. Isn't that great? Well, it's almost great. This specification was supposed to give us a loop. It was supposed to be the same as that specification, so I really have to add that there also. Adding it there, I now have to reprove my refinement. Well, in this case, if n equals 0, x gets 0 gives me this part, but for this part, I'm going to need to say y gets something. What? Well, when n is 0, the value I need is 1. And also for the else part, I have to reprove that, the else part. And so this keeps, as it was, it keeps x up to date properly by adding the right thing. But with variable y, I need to keep y up to date. If you don't, I'm trying to take you through this very quickly. If you try to prove this, you immediately discover this as you try to prove it. For the then part and for the else part, you say, wait a minute, y doesn't have the right final value. It needs something new too. Well, y gets y plus what? So it's 3n, this is 3n squared plus 3n plus 1, but I need to update that to for n plus 1 instead of n. In other words, I need the difference between 3n plus 1 squared, 3n plus 1, and this. All right? So that's 6n plus 6 by algebra. So now I know exactly what to fill in here. I guess I could say n plus n plus n plus n plus n plus n plus 6. But to be a little neater, I want to just neaten that up by saying, oh, I'll just call it z. And it'll be the right value because I'm just going to make this specification say it's the right value. Z primed is 6n plus 6. Oh, well, then I have to change this specification up there to say that. Now I have to reprove the first part. X gets 0 is fine, y gets 1 is fine, but z gets what? Well, when n is 0, z should be 6. And reprove the else part. That means updating z from 6n plus 6 to n plus 1 plus 6. Algebra says that's 6. Hooray, I can fill in the 6 there and I'm done. All right, what's the point of all this? Well, I could add a time variable, by the way, and prove that the time is n, but I don't want to take time to do that right now. What I really want you to notice is the role played here by formal methods. Okay? I started with a really simple idea. I just want a simple loop and it's going to be linear. All right? I'm going to use n equals 0 as a base. Fine. And so n is going to decrease towards 0. That was my entire thinking. After that, everything was dictated to me by the formal methods. Okay? I mean, I didn't start off saying to myself, I think I'll have a variable initialized to 6. You know? Why 6? I don't know why 6, but the formal method told me it had to be 6. Okay? So this is an example of formal methods helping you to write a program, not just verifying that you get every step correct as you go, but helping you to write a program. So in this cube example, I didn't actually use any loop constructs, but let me show you how loop constructs are handled. There was loops there, of course, but here is the standard version of loops if you take a semantics course. The while loop has to satisfy this equation, which says it has to be equal to its first unrolling. Now there's more than one solution to this equation, so this doesn't pin down the meaning of a while loop. But the other thing you need to say is that of all the solutions to that equation, the while loop is the weakest. This gives you the weakest fixed point, or least fixed point as it's called in the jargon. I have two complaints about the least fixed point definition of loops. The one is it's unusable. There's no way programmers can make use of it, and they don't. But the other is it's not even adequate. For example, it doesn't allow me to prove the perfectly reasonable fact that if the body of a loop doesn't decrease x, then the loop doesn't decrease x. But this is the standard definition of loops used in semantics. What I would prefer, oh, and if you add time, it gets even more complicated. That's what it is with time. I'm not going to take time to go through that. But anyway, what you learn in textbooks is about preconditions, postconditions, invariants of loops, and variants or bound functions, or it might be called well-founded sets. I don't know what you might have learned for proving correctness of while loops. And here is a standard sort of loop rule. Again, I'm not going to go through this because I don't want it. I'm just throwing up what might be familiar to you if you've ever taken correctness concerns or formal methods in a course. And again, even this is a little bit complicated, so what you end up with is a checklist, if you like. It says you have to find an invariant. That's usually tough. Check that the precondition implies the invariant. Check that the body of the loop maintains the invariant. You have to find a variant, which you then have to check that the body of the loop decreases the invariant, but not below 0. And then check that finally the invariant and the negation of the loop condition give you what you wanted in the end. This is the standard list of things to do. Okay, let's get rid of all that. If you have a while loop in predicative programming, you're going to use it to refine some specification. All right? W, some specification W. That just means that W is being refined by this. If the condition is true, then execute the body and repeat round the loop. Otherwise, you're done. And there's no loop notation here, and we already know what to do with an if then else, and what to do with a semicolon, and what to do with OK, so that's all we need. And that includes everything that was on the previous page, and everything that's already there in the usual way of teaching a loop. Now, if you happen to have a repeat loop, I don't know if programming languages have anymore, but they used to have things called repeat loops. What's the rule for that? I guess there probably was one for Pascal. I don't remember it particularly. All I remember now is that if I have a repeat loop, it's supposed to refine some specification. And that's exactly the same thing as saying that the specification is refined by this, which doesn't involve any loop notation. We know what to do with the notations that are there. And I sure don't remember any proof rule, if I ever did see one, for intermediate exits from loops. But a loop refines a specification, and I can quickly say what it means without using any loop notations. It means that first we execute A, and then if the Boolean is true, we're done. Otherwise, we execute the body and round the loop again. And then I know how to prove the correctness, even though I might not ever remember a proof rule for loops with intermediate exits. Or, just to make it more complicated, here's one with shallow exits and deep exits as well. I'm not going to go through with it, but it's the same thing that I've just been saying for all these others. In other words, any loop construct at all you can handle without having some new proof rule given to you. Even go-tos, but I'm running so late, so I'm going to have to skip over this part here and move along to the next example, binary search. What I really want to illustrate now is how do you come up with these specifications, and compare that to how you come up with invariants and other things for all those other assertions as well. So the problem is, given a non-empty sorted list L, assign natural variable h to say where x is, if it is there at all. So in binary search, you know how that proceeds. You've got some middle segment that's still to be searched. And in the outer portions, we already know that the item we're looking for is not there. So that's how it generally proceeds. And here is a simple program for binary search. You're supposed to know this already. So set h and j to be the extremes to start with. And as long as there's still something in the segment to be searched, set I to the middle value. And depending on the comparison, either h moves to the right, moves to the middle of the segment, or j moves leftward. So there we go, binary search. Now, I want to just move it apart a little bit here in order to put in the assertions needed to give you a Hoare-style proof. Those are the necessary assertions. I put in none that are unnecessary. Right here we see the invariant that we need. It's talking about the fact that in the outer portions, from 0 to h and from j to the end of the list, the list item we're looking for, x, does not occur. It's telling you what you know. We know that it's not out there. So that's what all that is about. And down here, it's the conclusion that says in the entire list, h tells us where x is, if it's there at all. In fact, if L of h is not equal to x, it tells us it's not there. Okay, so the variant we come up with is j minus h. Why j minus h? That's the size of the segment still to be searched. It's really the remaining execution time. That's what a variant really is. It's the remaining execution time. Okay, so that's the old Hoare style. How do you do it with predicated programming? Well, I'm going to need a specification for the entire thing. What is to be accomplished? And one for the loop. Those two specifications. Okay. And the proof obligations I can see those straight from the code that's there. I'm going to need to prove that A is refined by h gets 0 from the top line, j gets the length of the list, followed by b. The important thing to notice here is, to prove this top line, I don't need to know how b is being refined. I only need to know what is specification b, not how is it going to be refined. Okay. And b, again, also by looking at well, b is a while loop, so let's get rid of that, replacing it with the if-then-else. Okay. And this proof is just substitutions, replacing if and OK by their definition, same as we did before. Of course, we have to know what A and B are to make these proofs. So specification A is supposed to say what the binary search is to accomplish. So that's actually what we ended up with on the previous transparency, saying, where is X? Now, how do you come up with the specification B? Well, the good part of the story is, it's just like A, except it talks instead about the remaining interval from H to J. So this part is just like this part. A specification in general describes what is the purpose of a block, or what is it intended to accomplish. So what is that while loop intended to accomplish? Well, it's searching the interval from H to J. Okay. I forget this front bit, but that's all right, because as soon as I attempt to prove it, the proof attempt tells me I'm missing that bit. That's also a nice thing. In predicated programming, when the proof attempt fails, usually the failure actually tells you how to correct the specifications so that it will succeed. So that usually happens. Now, this is in contrast to an assertion, which summarizes for you what has been done, or says what's true at some location in the code. Okay, so it's quite different. There is no invariant here. For years and years and years, I've listened to speakers and textbooks and so on say, of course we need an invariant to prove something about a loop. You know, and I sit there choking because I know perfectly well you do not need an invariant to prove something about a loop. Invariants are hard to find. Okay. Okay. And variant, well, okay, if you want time, sorry, pointing to things. If you want time, you have to put a time variable in. Just somewhere in the middle of the loop will do. And then I can say that the time is bounded above by the log of the length of the list. And the proof is actually no harder than before, but of course you do have to know something about logarithms if you're going to make this proof. And the nice thing is, for free, I get the conjunction of all things proven so far. You get the conjunction. You don't have to prove that part. Okay. So let me compare assertions with specifications. An assertion says what's true at some strategic points. Specification says instead what some block of code is intended to do, what its purpose is. Yeah. Well, backing up to that, I have a conjecture, but I haven't got, you know, experimental data to prove it, that it's actually easier to say what's the second than the first. I think that if you look through programs, the comments you see usually describe what some block of code is there for, what it's intended to accomplish, rather than summarizing what's been done or saying what's true at that point. But I don't have the data to back that up. I think that the specification way of doing things is more like the way programmers actually do them. But one comparison that I can make is, well, right here, there's more assertions required by the old Hoare method than specifications required, 2 in this example. There's other technical difficulties if you've used the Hoare assertions that I won't get into, but I don't have those technical difficulties. And one advantage you've just seen already is that I can handle all kinds of loops and constructs yet to be invented without new proof rules for each of these. So these are reasons why predicative programming is better than alternatives. Okay. Now, it says we can talk about other things as well. Let me just get to non-termination. Here is the simplest non-terminating loop I could think of to write down. While true, do x gets x plus 1. Well, it's a loop. I want to worry about execution time because termination is just execution time. Termination means execution time is finite. Non-termination means execution time is infinite. So I stick a time variable in there to talk about execution time. And it's supposed to refine some specification. And I just get rid of the while loop, of course, in favor of if then else. And I can do a little algebraic simplification on if true then something, it just reduces to its then part. And as a matter of fact, that's what I would have written in the first place anyway for an infinite loop. I wouldn't have bothered writing the while loop. So x gets x plus 1, t gets t plus 1, and repeat. And now I'm wondering what might the execution time possibly be? Could it be 23? Let's see. T prime equals t plus 23 is supposed to be refined by x gets x plus 1, t gets t plus. This is really easy. It says replace t by t plus 1 right there. It says replace x by whatever, but there's no x, so that's even easier. So I end up with t prime equals t plus 1 plus 23. I end up trying to prove that 23 is equal to 24, and it isn't, and therefore I guess the execution time isn't 23. And it isn't going to be any other finite execution time that you might propose, not even complicated ones. I just tried a simple example here. The only one that's really going to work is this one. T prime equals t plus infinity, infinite execution time. Because when I replace t by t plus 1 right there, and replace x, but there is no x, and I end up trying to prove that infinity is equal to 1 plus infinity, and when you consult the laws that I use, it is. Infinity absorbs finite additions. So that's the solution. So I can prove non-termination in the case that we want for non-termination, which is something, by the way, that the old methods could not prove they seem to be limited to terminating computations. But non-terminating computations are very, very common. People write them a lot, and they want them. They're very useful. Okay, so that's all of that stuff. Look at that, I'm running out of time. Well, all right, I'm not going to do much more. I have what I'm going to show you is how general this is. So here's a problem, a complicated problem. We want the product of power series. So we want to write a procedure that reads an infinite sequence of coefficients on one channel. And and we're supposed to imagine that these are the coefficients of a power series, just like this. And in parallel, write an infinite sequence of coefficients on another channel. And they're the sequence of coefficients of another power series. And in parallel, to write on another channel, C, the infinite sequence of coefficients that's the product of the two power series that we read in, equal to the product. And we have to do this. One coefficient must be read each time unit and one written each time unit. So we got close time constraints on writing out the coefficients. So it seems like a fairly complicated problem. Now I'll show you the solution. I'm not going to walk you through this solution at all, but that's the whole thing. I will point out in this solution the parallelism. You can see the parallel lines there. So I haven't given you parallelism. Parallelism is actually very, very simple. It's just logical conjunction. Specifications in parallels, just logical conjunction. So it has plenty of parallelism in it. It's got a channel parameter up there. It's got local channel declaration down there. And it's got non-terminating loop. There's while, true, do. So it's an infinite computation. It's got dynamic process generation. Why? Well, because it's got a recursive call as one branch of a parallel composition. And that's the same thing as dynamic process generation without any new programming constructs. And it's got synchronization, which I'm not going to dwell on here, but it's also got dynamic storage allocation. Why? Well, because it's got declarations within a recursive call that's one part of a parallel composition. Anyway, the point is, this has got lots of interesting stuff in it, and it doesn't cause a problem for these formal methods at all. I'm going to have to prove two things. One thing corresponding to the whole procedure, and one corresponding to the loop that's within it. So I'm going to need a specification for the whole thing, the power series multiply. Oh, that's awfully easy. C equals A times B, where these are the power series. If my prover knows anything about power series, then it can make this proof. But if it doesn't, then I'm going to have to tell it what power series multiplication means. Or maybe I make this proof as a human, but that's what I need to know about the multiplication of power series. And then the loop, which I've written as a rather long identifier down there, it's actually much shorter specification. And then that's the other thing that I need to prove. So that's really all I'm going to say about it. But I'm going to say these formal methods, they really do apply to a large segment of the world of programming. And they really do scale up as well. A really great thesis, just a few years, well, 2006 here, by Yanis Kassios, extended predicative programming to object orientation, including all these features of object orientation. It's also been extended to pointer and heap specifications and non-interference by all of these people. And in fact, these people were implementing all of this stuff at Microsoft in Washington State. It's also, well, I'm going to tell you how this stuff becomes probabilistic programming on Monday, if you care to join me then. And it's also been used for quantum programming with a thesis here. So it's really been used for a great variety of things. Now, in case you didn't take in all the details of this during this talk, well, there's a book. And the best part about it is it's free. You can download it from my website. And it will give you all the details of this way of programming. Well, that's really it. Thank you very much. Any questions?